Section 1 Introduction. We're diving into the exciting world of multimodal artificial intelligence, AI, where visual, auditory, and text data come together. This field offers a wealth of possibilities, from personalized entertainment to advanced accessibility features. Natural language, as a powerful tool, can enhance our understanding and communication across different sensory domains. Large language models, LLMs, designed to understand and interact with human language, have shown impressive abilities in dealing with a wide range of AI models to tackle various multimodal challenges. However, a question arises: can these models also become creators of rich, dynamic multimedia content? Creating multimedia content involves producing digital media in various forms like text, images, and audio. Audio, a crucial part of multimedia, not only provides context and conveys emotions but also creates immersive experiences, guiding our auditory perception and engagement. In this study, we tackle a new problem: creating compositional audio with language instructions. This means automatically designing an audio storyline based on given text instructions and then creating corresponding audio content using different sound elements like speech, music, and sound effects. Previous works have used generative models to create audio context that aligns with specific conditions, such as speech transcriptions, music descriptions, and audio captions. However, these models often fall short when it comes to generating audio beyond these conditions, which is a requirement for real-world audio creation. Given the integrative and collaborative capabilities of LLMs, we ask, can we use the potential of LLMs and these expert audio generation models for compositional audio creation? Creating compositional audio presents challenges due to the complexities of synthesizing intricate and dynamic auditory scenes. Using LLMs for this task presents several challenges. 1. Understanding and designing context. LLMs need to comprehend textually described auditory scenes and design audio scripts featuring speech, music, and sound effects. Expanding the capabilities of LLMs in text generation to audio storytelling is a challenge. 2. Producing and composing audio. Unlike vision and language data, an audio signal is characterized by dynamic relationships among its constituent sound elements. Using LLMs to integrate various audio generation models to produce sound elements and compose them into a harmonious whole presents additional challenges. 3. Creating interactively and interpretably. Establishing an interpretable pipeline to facilitate human engagement is critical in automated audio production. It enhances creative control and adaptability, fostering human-machine collaboration. However, designing such an interactive and interpretable creation pipeline with LLMs remains an ongoing question. We introduce WavJourney, a system that uses LLMs for compositional audio creation guided by language instructions. WavJourney first prompts LLMs to generate an audio script, which follows a predefined structure. These audio scripts include the contexts of speech, music, and sound effects while considering their relationships. To handle complex auditory scenes, WavJourney breaks them down into individual acoustic elements along with their acoustic layout. By inputting the audio script into a script compiler, WavJourney generates a computer program where each line of code calls a task-specific audio generation model, audio I/O functions, or computational operation functions. The computer program is then executed to create the audio content. WavJourney offers several benefits. 1. It's creative. WavJourney can design audio scripts with audio storylines, diverse sound elements, and intricate acoustic relationships. 2. It's compositional. WavJourney can automatically break down complex auditory scenes into independent sound elements, enabling the integration of various task-specific audio generation models to create audio content. 3. It's training-free. WavJourney eliminates the need for training audio models or fine-tuning LLMs, making it resource efficient. 4. It's interactive. The interpretability offered by both the audio script and computer program allows audio producers with varying expertise to engage with WavJourney, fostering human-machine co-creation in real-world audio production. WavJourney pushes the boundaries of audio creation beyond traditional task-specific conditions and opens up new avenues for creativity in AI-guided content creation, AIGC. Our contributions are as follows. We present WavJourney, a system that uses LLMs for compositional audio creation. Given text instructions, WavJourney can create audio content with storylines that include speech, music, and sound effects, without the need for additional training. Through its decomposition paradigm, WavJourney can synthesize audio content aligned with complex text descriptions. The decomposed components provide WavJourney with interactive and interpretable rationale, facilitating human-machine co-creation. WavJourney demonstrates practicality across diverse real-world scenarios, including science fiction, education, radio play, and the dataset. To foster further research in AIGC for audio, we will release the code and software. Section Summary. The field of multimodal artificial intelligence, AI, combines visual, auditory, and textual data, allowing for personalized entertainment and advanced accessibility features. While large language models, LLMs, have shown great potential in solving multimodal tasks, the question remains whether they can also become creators of rich multimedia content. In this work, we introduce WavJourney, a system that leverages LLMs to automatically design audio storylines based on text instructions and create corresponding audio content using speech, music, and sound effects. WavJourney offers benefits such as creativity, compositional design, training-free operation, and interactivity, opening up new avenues for audio creation in AI. Section 2 Related Work. We're going to discuss two main topics: large language models, LLMs, and audio content creation. Firstly, let's talk about large language models, or LLMs for short. These are models like GPT-3 and Llama that have really pushed the boundaries of what we can do in the field of natural language processing, NLP. They're so advanced that they can generate text that's almost indistinguishable from something a human might write. Recently, these LLMs have started to show their worth as agents, capable of handling complex AI tasks. They do this by incorporating a variety of specialized AI models. Some examples of this are VisProg, which have shown how LLMs can break down complex tasks that involve both vision and language, like visual reasoning and generating images from text. These methods can create a computer program, like Python code, for each part of the task. These programs are then run one after the other to provide a solution that can be easily explained. There are also models that use LLMs as a sort of manager to control other AI models. These are used to solve tasks in language, vision, and speech. Similarly, there are models that connect multiple foundational audio models to solve tasks involving speech, music, sound understanding, and generation in multi-round dialogues. A lot of research has gone into using LLMs to solve tasks that involve multiple modes of input. However, there's still a lot we don't know about how LLMs can be used in audio content creation, even though this could be a big step forward for AI-generated content. Now, let's move on to audio content creation. This is a complex and dynamic process that involves many different parts, like content design, music composition, audio engineering, and audio synthesis. Traditional methods have relied on humans to do things like field recording, Foley art, and music composition, often alongside digital signal processing modules. In recent years, the intersection of AI and audio creation has become a hot topic. AI-driven methods, especially generative models, have shown that they're capable of synthesizing audio content for speech, music, sound effects, or even specific sounds like footsteps or a violin. Existing audio generation models usually focus on creating audio content based on a specific condition, like speech transcriptions, music descriptions, or audio captions. However, they're not designed to generate composite audio content that includes speech, music, and sound effects. Using data-driven methods to tackle composite audio creation is resource-intensive and not really practical. It would require collecting a complex audio dataset with corresponding text annotations and training powerful audio models. Section Summary. Large language models, LLMs, like GPT-3 and Llama have shown great potential in natural language processing, NLP, and have been used to address complex AI tasks by integrating domain-specific AI models. While LLMs have been successfully applied to vision-language tasks, their potential in audio content creation remains relatively unexplored, despite the growing interest in AI-driven approaches for synthesizing audio content. Existing audio generation models focus on specific types of audio, such as speech or music, and are not designed to generate compositional audio content with speech, music, and sound effects. Section 3 WavJourney. We've developed a system called WavJourney, which is a collaborative effort involving an audio script writer that uses large language models, LLMs, a script compiler, and a variety of audio generation models. These models include zero-shot text-to-speech, text-to-music, and text-to-audio generation models. Zero-shot text-to-speech refers to a system's ability to generate speech in a voice it hasn't been trained on, using an unseen voice preset as a condition. WavJourney's process can be broken down into two main steps. First, the audio scriptwriter takes a text instruction and modifies it with specific prompts. The LLM then uses these prompts to create an audio script that follows a structured format. Second, the script compiler turns the audio scripts into a computer program. This program is then run by calling the APIs of expert audio generation models to produce the audio content. The first challenge we faced when using LLMs to create audio content was generating an audio narrative script from text instructions that often only contain abstract concepts. To overcome this, we used LLMs to expand the text instructions into audio scripts, which include detailed descriptions of different acoustic contexts like speech, music, and sound effects. To manage the relationships between different acoustic elements, we prompted the LLMs to output the audio script in a structured format made up of a list of JSON nodes. Each JSON node represents an audio element, including its acoustic attributes like duration and volume. This allows us to break down a complex auditory scene into individual acoustic components, which we can then use to create the desired audio content with various domain-specific audio generation models. We've defined 3 types of audio elements: speech, music, and sound effects. Each audio element can be either in the foreground or the background. Foreground audio components are played one after the other with no overlap, while background audio can only be played alongside some foreground elements. Sound effects and music can be either foreground or background, but speech can only be foreground. Each audio component is represented by a JSON node in a list, and each node includes a text description of its content. To improve the listening experience, each audio component is given a volume attribute. Sound effects and music also have an attribute for length, allowing us to control their durations. For speech components, a character attribute is assigned, which lets us synthesize personalized voices later on, enhancing the narrative of the audio storyline. Thanks to advances in zero-shot text-to-speech, we can synthesize personalized speech based on specific voice presets in WavJourney. We use a set of voice presets designed for various scenarios, each manually annotated with descriptions of its characteristics and suitable application scenarios. We can then use the LLM to assign a suitable voice from the preset to each character in the audio script. To generate detailed and formatted audio scripts from text instructions, we wrap the text instruction in a prompt template. This template includes the specifications for each JSON node type, including the audio type, layout, and attributes. After receiving the generated audio scripts, we instruct the LLM to parse the characters in each speech node into personalized speech presets. The audio script with parsed voice mapping is then processed through the script compiler, generating the code for the next stages. Section summary. The WavJourney system is a collaborative system that utilizes language models to generate audio scripts, which are then compiled and executed to create audio content. The system uses prompts to guide the language models in generating structured audio scripts, which include detailed descriptions of speech, music, and sound effects. Additionally, the system leverages zero-shot text-to-speech technology to synthesize personalized voices based on specific voice presets, enhancing the narrative depth of audio storytelling. Section 3.2 Script Compiling and Program Execution. In Section 3.2, we discuss the process of script compiling and program execution. Our tool, WavJourney, uses a script compiler to automatically convert the audio script into a computer program. This process is outlined in the algorithm we've provided. Each line of code in the program triggers a specific audio generation model, audio input-output function, or a computational operation function like mixing or concatenating. Once the program is run, it produces a solution that can be easily understood for creating composite audio. Unlike previous studies that used language models, LLMs, to generate code, WavJourney uses LLMs to generate textual audio scripts. This approach makes it easier for audio producers who may not have programming skills to understand the process. Creating a computer program to compose complex auditory scenes involves a detailed series of steps in the code. These steps manage the calculations of audio length and the mixing or concatenation operations of audio clips. However, LLMs can sometimes be unpredictable and may not always follow the given instructions during the generation process. To address this, we introduced a script compiler to reduce the potential exceptions in the program workflow that could arise from the instability of LLMs. This helps to reduce uncertainty during inference. In Section 3.3, we discuss the concept of human-machine co-creation. The design of the audio script interface in WavJourney allows audio producers to actively participate in automated audio creation. By using the communication capabilities of LLMs, WavJourney enables users to personalize the audio content through multiple rounds of dialogues. We conducted several case studies on the dataset, and the results are provided in the appendix. Initially, WavJourney was asked to synthesize audio content based on the provided text descriptions. Then, through multiple rounds of dialogues, dynamic changes were made to the audio elements, such as adding new elements or modifying acoustic attributes. WavJourney's successful completion of these tasks shows its potential for interactive audio creation. By enhancing creative control and adaptability, WavJourney fosters a promising environment for human-machine co-creation in real-world audio production. Section Summary. The script compiler in WavJourney automatically converts audio scripts into computer programs, allowing for the generation of complex auditory scenes. By prompting language models to generate textual audio scripts instead of code, WavJourney improves comprehension for audio producers without programming expertise. Additionally, WavJourney enables users to actively engage in automated audio creation through multi-round dialogues, enhancing creative control and adaptability in real-world audio production. Section 4 Experiments. In our experiments, we use the GPT-4 model as the language model for our system, WavJourney. For generating music and audio from text, we use the best models currently available to the public. For text-to-speech synthesis, we used a model that can produce realistic speech that matches the tone, pitch, emotion, and rhythm of a given voice preset. To improve the quality of the synthesized speech, we used the VoiceFixer speech restoration model after the initial model. We processed audio signals at a sampling rate of 32 kHz. We wrote the computer program in Python. For controlling the volume of the generated audio content, we used the loudness unit full-scale, LUFS, standard. We conducted a case study using a dataset that contains 46,000 pairs of audio and text. We randomly selected several cases with complex captions, for example, more than 15 words, containing at least 3 sound events, to show how effective WavJourney is, compared to the best text-to-audio generation systems and Tango. The results and comparisons are shown in the appendix. We marked each sound event in the spectrogram with a colored line. The sound events in the audio generated by WavJourney are in the order described by the corresponding text. For example, 2 events happen at the same time when the word as is used, or one sound follows another when the word follow is used. Compared to the other systems, WavJourney was successful in generating all the sound events mentioned in the text description and arranging them in the correct temporal relationship, showing its ability to generate audio in a controlled way. We also conducted additional case studies using WavJourney in various scenarios, including science fiction, education, and radio play. The appendix shows examples of the generated audio script and audio content. The results show that WavJourney is practical for real-world audio production applications and has potential to make creating audio content easier. Section Summary. In our experiments, we used the GPT-4 model for WavJourney and publicly available state-of-the-art models for text-to-music, text-to-audio, and text-to-speech generation. We also applied a speech restoration model to enhance the quality of synthesized speech. We conducted case studies on the AudioCaps benchmark dataset and real-world scenarios, demonstrating that WavJourney outperforms other systems in generating sound events mentioned in the text and scheduling them in the proper temporal relationship, indicating its capacity for controllable audio generation. These results highlight the practicality and potential of WavJourney in audio content creation. Section 5 Limitations. Chapter 5 Limitations. Despite its ability to generate audio content from text instructions, WavJourney does have some constraints. These include 1. Scalability. WavJourney depends on structured audio scripts to depict sound scenes and script compilers to produce computer programs. This setup makes it challenging to enhance its functionalities. 2. Synthetic composition. The method of breaking down and reassembling audio can lead to artificial sounds that differ from natural sound patterns. This is especially noticeable in music composition, where the synchronization of beats, chord progression, and melody across multiple music tracks is necessary. 3. Efficiency. WavJourney's dependence on language models, LLMs, and various audio generation models results in considerable time expenditure when creating intricate audio content. Enhancing WavJourney's efficiency could make it more suitable for real-world applications. Section Summary. The limitations of WavJourney include its lack of extensibility, as it relies on structured audio scripts and script compilers, making it difficult to expand its capabilities. Additionally, the process of decomposing and remixing audio may result in synthetic audio that deviates from real-world sound distributions, particularly in music composition. Lastly, the reliance on language and audio models introduces significant time costs when generating complex audio content, highlighting the need for improved efficiency.